Alright, so this is Griffiths Quantum Mechanics, problem 3.7. And starting in part A, we're supposing that f of x and g of x are two eigenfunctions of an operator big Q with the same eigenvalue, the eigenvalue little q. Show that any linear combination of f and g is itself an eigenfunction of big Q with eigenvalue little q. Alright, so what we have here, we have this operator, big Q, alright, is going to operate on f of x, and because f of x is an eigenfunction of it with eigenvalue little q, and we just get this little q constant multiplied by the eigenfunction on the other side. And the same goes with g of x. Just like this. Alright, so now what we're going to look at is a linear combination of these, which we're just going to write it this way. So let's just call it h. How about, say, h of x is a linear combination of f and g. So I'm going to use a and b for the constants. So a times f of x plus b times g of x. Alright, so just a linear combination of f and g. So we are going to show that any linear combination is itself an eigenfunction of big Q. So we're going to show that this h of x is an eigenfunction as well of this big Q, and also with eigenvalue little q. Alright, so let's go for it. We just have big Q acting on h of x, right? And this is a linear operator that just can be sort of spread throughout this, or distributed, I guess, throughout this this side. Okay, so all we've done here is we've operated on this side and then operated on this side as well, and I just brought the constants out in front of this operator. Okay, well now we can look at this part and this part, which we have up here. So here we go. So we have the constant out front, and now we have this big Q acting on this f of x. Gives us little q multiplied by f of x right here, and the similar thing for this. So b, and then we have our little q, the eigenvalue here, and then our function g of x. Alright, so now what we can do is pull this q out, and we are left with a multiplied by f of x plus b multiplied by g of x. And I guess I could have, maybe I should have written this with this big Q out in front of this whole thing at first, but same thing anyway. Alright, so now we look at this piece right here and we say, oh, a times f of x plus b times g of x, that's just h of x. So here's our little q, our eigenvalue, and we are back to just an easy equation, just like these other two up here, where we have, where we show that h of x is an eigenfunction of this big Q operator with eigenvalue of little q. And that's exactly what we set out to prove, because h is a general linear function of these other two eigenfunctions. Alright, so there we go. That's for part A. Alright, for part B, we're going to check sort of a specific case of this. So suppose f of x is equal to e to the x, okay? And g of x is equal to e to the minus x. We're going to check that these are eigenfunctions of the operator, of which I'm just going to use q here again. But the operator this time is just the second derivative with respect to x. And so we're going to check that these two are eigenfunctions of this operator with the same eigenvalue. And then we're going to construct two linear combinations of f and g that are orthogonal eigenfunctions on the interval -1 to 1. All right, so here we go. Let's just look at this operator acting on f first. All right. So that's just the second derivative with respect to x of e to the x. All right, and take one derivative, this stays the same. Take another derivative, it stays the same again. So this is just equal to e to the x, all right, which is equal to f of x, all right? And so imagine we have 1 right here, right? 1 is the eigenvalue for this eigenfunction, all right? So now we want to check the other one. D squared, d, oh, I forgot 2 there. Yeah, this time we have e to the minus x, all right? All right, so when we take one derivative of this, we'll end up with a minus e to the minus x. Okay, we may have space to write that. So I'm going to take one derivative. So now this is just a one derivative that's left. And now we have a minus e to the minus x, okay? And that is, taking this other derivative will bring down another minus sign, and we are left with just e to the minus x on this side, which is g of x from right here. And again, there's the constant out front is just 1 again. So 1 is the eigenvalue for g, and 1 is the eigenvalue for f when we have these two functions, or f and g are these functions, and we have this operator, which is just the second derivative with respect to x. Okay, so we have shown that f and g are eigenfunctions of this operator with the same eigenvalue, which is 1. So I'm just going to write the little q equals 1. All right. So now we're going to construct two linear combinations of f and g that are orthogonal eigenfunctions on the interval -1 to 1. Okay. The quick answer is just one of them is e to the x plus e to the minus x, and the other one is e to the x minus e to the minus x. All right. These two are orthogonal, and when you integrate them, but let's go into this in a little more detail, maybe, and maybe a little bit more general. All right. So, just for sake of notation, I'm just going to call one C1 and one of them C2, and I'm going to leave it completely general, so I'm just going to use 4 different constants. Like this, C to the x, like that, okay? And on the interval, what we want to show on this interval from -1 to 1 is that, I guess using this, we'll use the complex conjugate for one of these. All right, we still have generality because you can just switch these labels if you want at this point. All right, so for orthogonality, we want to show that this inner product is equal to 0, okay? So here we go. Let's just launch into this. So looking at C1 star, so we'll have an A star e to the x plus a B star e to the minus x, okay? So that's this guy right here. Now we will look at this other guy, C2, and we didn't take the conjugate of him, so e to the x plus d to the e minus x. Okay, here we go. Okay, so we have an A star multiplied by C, just taking this first product here. Okay, and then taking the product of these guys, this e to the x and multiplied by e to the minus x, that's just going to divide out, right? So we just have a B star C, okay? And then this product, same thing, the e's will divide out. We have an A star D. And then we have this final one, which is a B star D e to the minus 2x. Okay. All right, here we go. Let's go ahead and take this integral. All right, and remember we're setting all of this equal to 0 if we've lost track of the equal sign, right? Because we're looking for orthogonality. Okay, so let's see what we have. I'm just going to, so we have an A star C, and then we have an E to the 2x, and that's divided by 2. So for the integral of this first piece here, plus B star C multiplied by x, plus A star D, also multiplied by x, because these are just constants, right? Integrate them, you get an x, plus B star D e to the minus 2x, and then we're dividing by minus 2, okay? All right, and this is evaluated from minus 1 to 1. Okay. All right, so one thing we'll see first is these two guys are going to go away, because you'll have a 1 minus, are they going to go away? Maybe they're not. Okay. Yep, I think I made a mistake earlier when I did this. Okay. We'll still do this. So let's see what we have here. So we have an A star C e to the 2 over 2 minus, okay, I'm just going to bring that A star C out to the front, e to the minus 2 over 2. All right. I'm definitely going to run out of room on this. Let's just start on a new page real quick while we still have a chance. Okay, so I'm just going to copy this again. So A star C, I'll bring the 2 out here as well. So e to the 2 minus e to the minus 2. Okay, so that's just this term. Okay. All right, plus B star C, and then a 1 minus a minus 1. Okay, which is just plus. And then the same for the next term, which is this A star D And same thing again, a 1 plus a 1 minus a minus 1, right? So that's just a 2. I'm just going to combine this into 2. Okay, and then this last one, where, well, let's see what we have here. Well, we'll have a B star D. And then 2. And then let's go ahead and reverse the limits of integration and get rid of this minus sign. So we have an e to the 2 minus an e to the minus 2. Okay, I hope I did that right. Yeah, I think I did. Okay. Alright, and then we're setting this all equal to 0. So all we're looking for here are the constraints imposed on these constants A, B, C, and D in order to have orthogonality. Okay. All right. So let's multiply everything by 2. So we have an A star C, and then I'm going to go ahead and factor. I'm going to gather the terms of this guy. Okay, yes. Okay, so here we go. This is an equation that must be satisfied if we want our two functions to be orthogonal to each other. So just real quick, let's look at this the quick case that we talked about right at the beginning and just make sure it works. So in this case, we had, let's say, A equal to 1, B equal to 1, C equal to 1. All right, there's a 1 in front, 1 in front, 1 in front, a minus 1 in front right here. So a D equal to minus 1. So let's just check that real quick. So AC, all right, so this is a 1 minus 1. Okay, that gives 0, right? So this whole term is 0. And this is B and C, okay, that's a plus 1, so we have a 2 here. And then A times D, that's a minus 1, so we have a minus 2, all right? So we do see that our original quick response here is a solution to this. And suppose, all right, suppose real quick that we also wanted to find orthonormality. Well, let's see, for that we want the norm squared of A and B. So basically this A plus B has to be equal to 1, okay, and same for C plus D. Okay, because if you take the inner product of one of these with itself, then you want to get a 1 here instead of a 0. If you take the inner product with the other one, then you want to get 0. Okay, let's see. Is there anything better we can say about this? It's a little bit, seems a little bit specific to this particular problem. Okay, so before like if we were to normalize these, right, we would get we'd divide everything by a square root of 2, right? So this would be if we didn't want only the orthogonal case, we wanted orthonormal case, right, to satisfy these equations as well. Right, square them, you get 1/2 plus 1/2 equals 1, all right?